Compressors are the heart of every air conditioning system, but to keep that heart running, we need a capacitor. And when a capacitor fails, so does the compressor. When the compressor fails, you no longer have cold air. So what is it about this $20 part that plays such a critical role in keeping us cool in those really hot summer days? Now, motors in heating and air conditioning systems in residential applications work on a rotating magnetic field, but to understand how that works, we need to start at a power plant. Now, just a little side note here, before I was in heating and air conditioning, I used to actually run a power plant. This is my old workstation, just like Homer Simpson. Electricity is generated at power plants using massive turbines connected to generators. Now, inside these generators, coils of wire move through magnetic fields, which produces electricity. This setup creates three separate voltage waveforms, and this is called three-phase power. Now, this three-phase power is sent out through high voltage transmission lines, often hundreds of thousands of volts. But once it gets closer to a town, the voltage is lowered down by a step-down transformer to around 7,000 volts or so. Now, on your street or power pole, there is a distribution transformer, and those are the gray cans we see up on the telephone poles. Now, that transformer just connects to one of those three phases, and it steps it down to 240 volts. Two power legs, each 120 volts, along with a neutral wire. And this is the power that's actually ran to a home and to the electrical panel. Now, behind all those breakers, we have two bus bars, and each 120 volt leg from the transformer out in the telephone pole connects to each bus bar. Now, you can see in the middle, these bus bars have this sort of overlapping pattern. And that is because when you put a double pole breaker into an electrical panel, each terminal of that breaker is touching a separate bar. And so that breaker on each terminal is putting out 120 volts on both terminals, 120 from one bar and 120 from the other bar. And this is the 240 volts that we send to our compressor, where all the magic happens to create cold air. But we still have one major problem to overcome. Even though we have power going to our compressor, we still don't have what we need to make that compressor spin and move refrigerant through the system to create air conditioning. When a current flows through a wire, an alternating current actually changes direction back and forth on the same wire. Now, we can create a graph of this behavior, which is what we call a sine wave. Now, the best way to think about a sine wave, and this might not be 100% technically accurate, but imagine a current flowing in one direction and it picks up maximum velocity. But in order for it to reverse direction, it has to slow down and come to a stop and then start moving the other way. And when it starts moving the other way, it builds up momentum again, but eventually has to slow down and stop again in order to reverse direction. And so we can see this behavior on our sine wave. As the current flows in one direction, it builds up maximum velocity until it peaks. It then has to slow down and come to a stop. Once it comes to a stop, it reverses direction, picks up maximum velocity again, which is called the trough. It then has to slow down and come to a stop. And this cycle just keeps happening over and over and over again. Now, an interesting thing happens when we run this current through a winding in a motor that's wrapped around an iron core. We can create a magnetic field. And so when we have a current flowing in one direction and it hits a maximum velocity, we can create a magnetic field that has, say, a northern polarity to it. But as that current slows down and comes to a stop, our magnetic field breaks down and disappears. But when the current starts flowing in the opposite direction, a magnetic field begins to build up again, only this time it has a southern polarity. Now, that magnetic field will also break down and disappear. And this just keeps happening over and over again. So when a current runs through a single winding in a motor, we have a magnetic field that's flipping back and forth in polarity. But this flipping back and forth is a linear pattern. It's not that rotating magnetic field we need to actually spin a motor. Now, residential compressors and other types of motors don't have just one winding. They have two, a start and a run. Now, each one of these windings has a 120 volt hot leg running through it. So what we have are two sine waves, each one creating a magnetic field. But we still have a problem. When you take a single phase off of the transmission lines, like we did at our transformer out on the utility pole outside of the house, and then you split that phase into two hot legs, 120 volts each, What we end up with are two sine waves that are completely the opposite of one another. They're 180 degrees apart from one another. And so what this means is as one coil or winding is creating a magnetic field with a northern polarity, the other winding is creating a magnetic field with a southern polarity. Now this still creates this linear pattern. We have two magnetic fields, but they're still just flipping back and forth and kind of canceling each other out. We still don't have a rotating magnetic field. Now this is where a capacitor steps in and saves the day for us. Now earlier I stated that a compressor gets two legs of power, 120 volts each. Now one of these legs of power runs through a capacitor. Now power does not actually flow through a capacitor. As you can see, we have two separate plates that have a space in between them. So what happens is when a current flows into a capacitor, let's say on the common terminal, and it flows into that plate gets an excess of negative charges on it. Now what this does is it pushes the negative charges off of the opposite plate, and that charge gets pushed down the wire as a current. So even though electricity doesn't flow through the capacitor, the effects of a current do transfer through. Now the current is going to reverse direction. So as the current going into the common side of the capacitor starts to reverse, it pulls the negative charge off that plate, creating an excess of positive charges. And so what that does is it affects the other plate by pulling negative charge into that plate, and the current reverses on the opposite wire. And so we still have this back and forth effect of the current going through the capacitor. But in the time it takes the capacitor to build up this charge and then discharge it, creates just enough of a time offset in the sine wave. Now what this does is that the two sine waves that go through the windings in the motor are now no longer 180 degrees apart. They are now 60 to 90 degrees apart. Now as both currents flow through both windings of the motor, you have one current that's building up a northern magnetic field, and the other one, because it's only 90 degrees behind, is also going to start building up a current of the same magnetic field. So we'll have north, north, south, south, north, north, south, south, and they're offset just enough that it creates a rotating magnetic field in a circular pattern. When capacitors fail, we no longer get that perfect offset in the timing of the sine wave. We don't get those complementary magnetic fields, and they go right back to canceling each other out, which is why a motor will hum, but it won't spin and do anything.